Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 652, Find Duplicate Subtrees. Before we do that, I just want to ask you to please subscribe to my channel. I want to make this channel grow and make more content for you guys, so please subscribe so the videos keep coming. Anyway, let's read the question prompt. Given the root of a binary tree, return all duplicate subtrees. For each kind of duplicate subtrees, you only need to return the root node of any one of them. Two trees are duplicate if they have the same structure with the same node values. Cool. So let's look at an example. Which are the duplicate subtrees in this tree? Well, from visual inspection, we can see that there's actually two duplicate subtrees. So the first is going to be just the node 4, and then we're going to have the tree which is rooted at 2 and has a left node of 4, and that appears twice here. So the two duplicate subtrees in this tree are going to be the tree rooted at 4, and so that's going to be the node 4, and then we're going to have the one rooted at 2, right? And then its left tree is going to be 4. So in this problem, there are two subtrees, and it's going to be this. So we want to return it. But how do we actually solve this question? Well, what we want to do is actually quite simple. What we're going to do is we're going to do a post-order depth first search. And we want to do this in a bottom-up manner. So we're going to start at the bottom, and what we're going to do is we want to basically hash the tree that we've seen so far. So we're going to maintain a hash map, which basically keeps track of our tree. Now, the nodes that we're given are not hashable. So what we need to do is we need to figure out some representation of how we're going to represent the tree that we've seen in a way that's hashable. So what we want to do is essentially, if we have a node, right, we'll, say it's 4, and if it has a left child, then we can add that left child, and if not, we'll use like a hash to signify null, and that way we can actually write out what our subtree is. So for example, let's say this tree 3, right? So it would have a root of 3, its left would be 2, its right is 4. Now the right of the node 2 is going to be 4, and it doesn't have a right child, so it's hash. Now what about the 4? The 4 doesn't have any child, so that's going to be hash and hash. And that way we can have a string representation of our tree so far. That way we can do a lookup every time we obtain one of these representations in our dictionary, and if it already exists, we can add a +1 to our counter of the amount of duplicate subtrees we have, and that way we can actually figure out our count of the duplicates is by basically maintaining this like string representation, and as we go up the tree, basically adding to it, and we will build this until we get to the root, and at that point we'll have finished our DFS and we can simply return our values. So now that might seem a little bit complex, but let's go to the code editor. We'll type this out line by line, and I'll explain to you exactly how we do it, and it should become a lot clearer. This is just a general idea of the algorithm, and I don't want to get too messy with the drawings, so I'll see you in the code editor momentarily. Okay, we're back in the code editor. Let's write this up, and I hope I don't mess it up this time, because this is the third time I tried to record this, and each time I've made a mistake, so hopefully I get it right this time. Anyway, the first thing that we want to do is define our result data structure, which, as we can see from the type hint here, needs to be a list, right? So we're going to define our empty list to store a result. And if you recall from the diagram that we drew, we're going to be keeping a map which maps the string representation of our tree path to, we're going to map it to the actual count of how many times we've seen that path, so we can know whether or not we've seen a duplicate or not. So we're going to say tree map, and this is just going to be an empty dictionary. Now what we need to do is define our depth first search function. So we're going to say def dfs. This is going to take our node and our path. And I apologize if earlier I said that we're going to do this in a post-order manner. We're actually going to do it in a pre-order, and it's going to be a top-down, not bottom-up. I'm not sure what I was thinking earlier, but it's going to be a pre-order, basically top-down solution. So what do we want to do here? So we want to basically check that we actually have a valid node, because obviously we want to be checking the left and right children of our node, and if our node is null, then we're going to be returning nothing there, right? If we try to access the left or right of a null node, we're going to get an error. So we need to make sure that we actually have a valid node. So we're going to say if not node. All we want to do is just return a hash, and that's how we're going to actually symbolize that we have a null node for our path. Now what we need to do is we need to actually update the path. So we're going to say path, and we're going to say plus equals. So what do we want to do here? So we want to separate each of our node values by a comma, and what we're going to do is now we need to join. And the things that we're going to join, we're going to take the string value of our current node, and we're going to, then add to it the string representation of the left subtree, and then the string representation of the right subtree. So we're going to call DFS on our node.left, passing in the current path, and then we also want to call DFS on node.right and passing in the current path. So that is how we're going to update the path with whatever happens in the children. Now what we want to do is we want to check whether or not we've seen this path before. So we're going to say if path in tree map, then what we want to do is we want to increment the amount of times we've seen it. So we're going to say tree map of path, we're going to add 1 to it. And now what we want to do is actually check whether or not this is a duplicate. So the only time that we want to add our, something to our solution is if the path count actually equals to 2. And the reason for that is because if it's 1, obviously it's the first time that we see it. If it's 2, that means that we've seen it again. Therefore, we need to add it to our result. Anything after 2, we've already added it to our result. There's no reason to add it again because we don't want just every single instance. We just want unique values. So our result basically should just have the unique duplicate subtrees. So we're going to say if tree map of path equals to 2, then that means that this node that we're currently at is a duplicate, has duplicate subtrees. So we're going to say res.append our node. Otherwise, if we haven't actually seen this, so this is the else on this block, we just want to say tree map of path equals to 1. So if we've never seen it before in our tree map, then we just want to add it to our map and set its count equal to 1. And the last thing that we want to do is basically return the path so that way the next iteration can use it. Because obviously we're doing this recursively, so we're going to be passing it up the kind of recursive stack so that way the next level can use our path here. So that is the DFS function. Obviously, to get a solution, we need to call our DFS function. So we're going to call it on our root, and we have not had any path so far because we haven't processed any nodes. So our original path is an empty string. And now at the end, all we need to do is just return our answer. Oops, sorry, res. So let me just run this, make sure I didn't make any syntax errors again, and okay, we are good. So let me submit this, and it works. Brilliant. So what is the time and space complexity of our algorithm? Well, we know that this is, if I could just click here, we know that this is going to be a depth first search traversal through our tree. So this is just going to be big O of n. It's going to take, depending on the amount of nodes in our tree, it's going to be big O of n. We have to traverse every single node. So time complexity, big O of n. What is the space complexity here? Well, obviously we're doing a DFS. So it's going to cost big O of n time to actually perform the recursion. So that's going to be big O of n. And then maintaining the tree map, it could be the case that every single subtree in our tree is actually unique. So therefore it's going to be big O of n, or it just depends on the number of nodes in the tree is the amount that we're going to have to store in tree map. So it's going to be big O of n plus big O of n, but we know that this is just equal to, 2n, which asymptotically is the same as big O of n. So that is your time and space complexity. Quite a fun problem. I quite like these DFS traversals through binary trees. Find them quite fun, and luckily the code is not that complicated. As you can see, it's a pretty standard DFS traversal. So that is how you solve this question. If you enjoyed this video, please leave a like and a comment. It really helps with the YouTube algorithm. If you want to see more content like this, please subscribe to the channel. There's a lot more videos coming. And otherwise, thank you so much for watching, and have a great rest of your day.